Hi, this is Jason Molesky. In this example, we'll take a look at constructing a confidence interval for a population mean. A manufacturer of high-resolution video terminals must control the tension of the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow for wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. In the blue box, we see the tension readings from a random sample of 20 screens from a single day's production. Our problem is to construct and interpret a 90% confidence interval from the mean tension mu of all the screens produced on that day. In order to construct that confidence interval, a one sample t interval to estimate mu, we'll need to check our conditions. Well, first of all, the randomness condition. We're told the data come from a random sample of 20 screens produced that day, so that condition is met. Since we're constructing a confidence interval for mu, we also need to check to see whether or not we have a large sample. Ideally, we'd like our sample size to be greater than 30. Now note here, the sample size is small, it's only 20, so we'll need to check whether or not it's reasonable to believe that the population distribution is normal. We have no idea what the population distribution looks like, so what we'll have to do is examine the sample data. And if the sample data doesn't give us any reason to suspect the normality of the population distribution, then we can assume our large sample condition or our normality condition is met. Well, in looking at the sample data, we can either look at it in terms of a dot plot, or we can look at a box plot, and we can see that neither the dot plot nor the box plot shows a strong skewness or any outliers. Further, a normal probability plot of these sample data is roughly linear, so the graphs give us no reason to doubt the normality of the population. Therefore, our conditions are met, and we can proceed in constructing a one sample t interval. Now, we used our calculator to find the mean and standard deviation of the tension readings for these 20 screens. Our x bar is 306.32 millivolts, and the sampling standard deviation is 36.21 millivolts. We used the t distribution with 19 degrees of freedom to find the critical value. From table B, this critical value is 1.729. So, the 90% confidence interval for mu is given by this formula. X bar plus and minus t star times the sample standard deviation divided by the square root of n. Plugging in our values and solving, we get an interval of 292.32 to 320.32. So to conclude, we're 90% confident that the interval from 292.32 to 320.32 millivolts captures the true mean tension in the entire batch of video terminals produced that day. For some additional practice in building a confidence interval for mu, try exercise 69.